You're young. Maybe 25. A lifetime stretches before you, 60 years, perhaps more, to breathe, to think, to simply be. Now, imagine stepping onto the fastest ship humanity can ever build. You wave goodbye. The engines roar. Earth shrinks beneath you, a blue marble fading into the vast, indifferent dark. You have one lifetime to travel. Just one. So, when your journey ends, decades from now, after endless black, how far will you have gone? What is the absolute farthest you could realistically travel from Earth? Let's find out. Before we ask how far a human life can reach, we must understand the ground we stand on. Or rather, the emptiness we float through. The night sky, from Earth, looks crowded. Stars scattered just beyond the clouds, a handful of shimmering jewels. That's an illusion. A trick of distance, compressing immense gulfs into tiny points of light. In truth, the universe is built on void. Like a desert of sand, it is vast, continuous, and almost entirely empty. Let's start close to home. Leave Earth, accelerating outward. The Moon, our nearest neighbor, floats about 384,000 kilometers away. A commercial jet would take weeks to reach it. The fastest spacecraft ever built? Less than an hour. That sounds impressive, doesn't it? Until you grasp the scale, the Moon is barely a step outside our front door. Beyond it lies Mars, sometimes a mere 56 million kilometers away, sometimes much farther, depending on our planet's cosmic dance. Then Jupiter, a gas giant so vast it could swallow Earth over 1,000 times. Then Saturn, ringed and regal, distant in the night. And finally, Neptune, orbiting so far from the Sun that its sunlight is a faint, eternal twilight. Even the outermost edge of our solar system isn't a neat boundary. Our Sun constantly blasts a stream of charged particles outward, creating a colossal magnetic bubble, the heliosphere. This bubble stretches billions of kilometers in every direction, far beyond the planets. Only when you cross that invisible frontier do you truly enter interstellar space, the realm between the stars. Voyager 1, launched in 1977, took 35 years to reach that threshold. Decades of travel, just to take a single step beyond the Sun's direct influence. And Voyager is still astonishingly close, in cosmic terms. If our solar system were the size of North America, Voyager would still be standing on the front lawn. This is the first stark reality we must face. Escaping even our own stellar neighborhood is not trivial. It takes years, sometimes decades, at the fastest speeds humanity has ever achieved. Now, widen that scale. The nearest star system to us is Alpha Centauri. It's about 4.37 light-years away. A light-year isn't a measure of time. It's a measure of distance. It's how far light, the fastest thing in the universe, travels in one Earth year. Light moves at 300,000 kilometers per second. In a single one of those seconds, light could circle our planet 7 times. In 1 year, it travels nearly 9.5 trillion kilometers. Alpha Centauri is 4.37 times that immense distance. To truly grasp this scale, imagine shrinking the Sun to the size of a marble. On that scale, Earth would be a tiny grain of sand, orbiting a few feet away. Alpha Centauri would not be across the room. It would be thousands of kilometers away, another marble in a distant city. The stars are not sprinkled nearby. They are separated by gulfs so vast that even light, the universe's ultimate speedster, takes years to cross them. And that brings us to the core of our question: speed. Distance alone doesn't define how far you can go in a lifetime. Speed does. Double your speed, and you double your reach. Increase it tenfold, and your reachable universe expands tenfold. Speed is the ruler by which your lifetime is measured against the cosmos. So, what's the fastest we've ever traveled? The Parker Solar Probe, humanity's current speed record holder, reaches about 430,000 miles per hour. That's fast enough to circle Earth in minutes, fast enough to reach Mars in a matter of days. But compared to light, it's crawling. Light moves at roughly 671 million miles per hour. The Parker Solar Probe travels at less than 0.1% of that speed. It's like comparing a sprinter to a lightning bolt. If you traveled continuously at that record-breaking speed for 60 years, you would cover roughly 226 billion miles. That sounds immense. It is not. Alpha Centauri is about 25 trillion miles away. At the Parker Solar Probe speed, 60 years of relentless travel wouldn't even cover 1% of that distance. You would spend your entire lifetime moving outward, engines burning, yet still be firmly inside the sun's wider neighborhood. Closer to home than to the nearest star. This is where intuition fails. On Earth, distance feels conquerable. Oceans in hours. Continents in minutes. The planet's circumference, manageable. But interstellar space is not scaled for human intuition. It is scaled for light. To reach Alpha Centauri within 60 years, you'd need to travel at about 7% of the speed of light. Not 0.07%. 7 full percent. That is more than 100 times faster than any spacecraft we have ever built. And Alpha Centauri is just the closest star. Beyond it lies Barnard Star, at about 6 light-years. Sirius, at 8.6 light-years. Vega, at 25 light-years. Each additional step outward demands even greater speed if you hope to arrive before your lifetime expires. This is the geometry of mortality in space. Your lifespan is a fixed line segment. The universe is an expanding plane. The only way to extend your reach is to move faster. But speed comes at a cost, an enormous one. As you push toward even a small fraction of light speed, energy requirements don't just rise, they skyrocket. It's like trying to climb a mountain that grows taller as you ascend. And even if you solve the energy problem, other challenges appear: radiation, microscopic dust grains that become high-velocity bullets, the need to accelerate gently enough for the human body to survive, the necessity of slowing down when you arrive. Reaching another star at extreme speed is useless if you cannot stop. Every solution creates another constraint. And yet, within these constraints, there is still possibility. If future propulsion systems, perhaps nuclear fusion, could push a spacecraft to 10 or 20% of light speed, then 60 years would allow you to travel 10 to 12 light-years, perhaps more. That would place dozens of nearby stars within reach. Not the galaxy. Not even a meaningful fraction of it. But a local cluster, a small cosmic neighborhood. The Milky Way is about 100,000 light-years across. A 20 light-year radius is a speck inside it. If the galaxy were the size of North America, your lifetime would allow you to explore a single city block. But that city block contains real suns, real planets, potentially real life. This is the first great revelation: a human lifetime is not enough to cross the galaxy. It is barely enough to cross the gap to our nearest stellar neighbors, even if we develop technology far beyond what we possess today. And yet, it is not zero that matters. For all of human history, the stars were unreachable by definition. They were lights on a dome, symbols, stories, navigation points. But in the language of physics, they are no longer abstract. They are coordinates. The distances are brutal. The speeds required are extreme. The energy demands are staggering. But the math does not say never. It says only this far. And that is where our journey truly begins. Once you understand the scale of the distance, everything reduces to a single word: speed. In space, speed is destiny. It determines not just how far you can travel, but whether you reach anything meaningful at all. Your lifetime is fixed, perhaps 60 years of active travel. The only variable left is how quickly you can move through the dark. On Earth, increasing speed feels straightforward: build a stronger engine, burn more fuel, improve aerodynamics. But rockets are not airplanes, and interstellar space is not the sky. The deeper truth of rocketry is hidden in a deceptively simple principle known as the rocket equation. Every rocket carries its own propellant. To move forward, it throws mass backward. The faster you want to go, the more propellant you must eject. But propellant has weight, and weight requires more propellant to accelerate it, which adds more weight, which demands more propellant. It becomes a spiral. Imagine trying to sprint while carrying a backpack full of fuel, except the backpack gets heavier every time you decide you want to run faster. At some point, you're no longer accelerating yourself, you're accelerating the fuel needed to accelerate the fuel needed to accelerate you. Chemical rockets, the kind that lifted humans to the moon, are astonishing achievements of engineering. They're powerful enough to escape Earth's gravity and roam the solar system. But they are fundamentally limited by chemistry. Burning hydrogen and oxygen releases a fixed amount of energy per kilogram. That energy density simply isn't high enough to push a large spacecraft to even 1% of the speed of light without requiring absurd amounts of fuel, more than could physically exist. Interstellar travel is not an engineering inconvenience for chemical rockets. It is a mathematical impossibility. So, we turn to better engines. Ion drives are often described as futuristic, but they're already real. They work by ionizing atoms, typically xenon, and accelerating them using electric fields. Instead of a violent explosion, like a chemical rocket, they produce a steady, whispering stream of high-speed particles. Their exhaust velocity is much higher than chemical engines, meaning they use propellant far more efficiently. But efficiency is not the same as power. Ion drives push gently. The thrust is tiny, fractions of a millimeter per second. Over months and years, that gentle push builds remarkable speeds for small robotic probes. But for a crewed spacecraft, with the mass of life support systems, shielding, and structure, that gentle push becomes almost symbolic. It would take decades just to reach modest fractions of light speed, if the fuel mass problem could even be managed. And that brings us to the threshold where interstellar travel becomes plausible: nuclear energy. Nuclear reactions release millions of times more energy per kilogram than chemical reactions. Instead of rearranging electrons in molecules, you're reshaping atomic nuclei themselves. It is the difference between rearranging bricks and altering the structure of the bricks' atoms. A nuclear thermal rocket uses a reactor to heat hydrogen to extreme temperatures and expel it for thrust. These engines were actually tested in the 1960s under NASA's NERVA program. They worked. They produced higher exhaust velocities than chemical rockets. They could, in theory, shorten travel times within the solar system dramatically. But even nuclear thermal propulsion likely caps out at a few percent of light speed. Better than chemistry, but still not transformative enough to make Alpha Centauri an easy journey. Then there is nuclear pulse propulsion, most famously envisioned in Project Orion. Instead of a steady burn, Orion proposed detonating small nuclear explosions behind a spacecraft, each blast pushing against a massive, shock-absorbing plate. It sounds reckless, even apocalyptic. But on paper, the physics worked. A large Orion spacecraft could, in theory, reach several percent of light speed. Several percent. That is enough to make interstellar travel possible within a century, but still marginal within a single lifetime. To reach 10% of light speed, a speed where a 60-year journey spans roughly 6 light-years, you likely need something more powerful still: nuclear fusion. Fusion is the process that powers the sun. Instead of splitting heavy atoms like uranium, fusion combines light atoms such as hydrogen, releasing even more energy per unit mass. In principle, a fusion rocket could achieve exhaust velocities high enough to reach 10 or even 20% of light speed. If that becomes possible, the map changes. At 10% of light speed, 60 years carries you about 6 light-years. Barnard Star becomes reachable. Wolf 359, a dim red dwarf, lies within range. At 20%, you extend to roughly 12 light-years. Now you are surveying dozens of star systems. The nearby stellar neighborhood opens like a cluster of lanterns within walking distance, cosmically speaking. But fusion propulsion is not yet a reality. We have not even built a practical fusion power plant on Earth, let alone a compact, space-worthy fusion engine. The engineering challenges are immense. You must contain plasma hotter than the sun's core. You must channel that energy into directed thrust. You must shield the crew from radiation. And you must do it reliably for decades. Each layer of possibility rests on technology that does not yet exist. Beyond fusion lies antimatter, the most energy-dense fuel allowed by physics. When matter meets antimatter, the conversion to energy is nearly total. Theoretically, antimatter propulsion could push spacecraft to large fractions of light speed without absurd fuel masses. But antimatter is not lying around, waiting to be scooped up. It must be manufactured in particle accelerators at enormous energy cost. Current production rates are microscopic. To accumulate even a kilogram would take longer than the age of civilization. And storing antimatter safely, preventing it from touching normal matter and annihilating, is an engineering nightmare. So when we speak of speed, we're not speaking casually. We are speaking about energy densities that rival stars, engineering challenges that stretch decades into the future, and physical limits that do not negotiate. There is also the human body to consider. Even if you had unlimited energy, you cannot simply accelerate indefinitely. The human body can tolerate about 1 Earth gravity, 1 g, comfortably for long periods. Accelerate faster, and blood begins to pool. Organs strain. Consciousness fades. At 1 g of continuous acceleration, you could reach 10% of light speed in about a month. That sounds promising, until you remember you must also decelerate for another month at the other end. Acceleration and braking consume precious time from your 60-year window. They also consume energy. Everything in interstellar travel is a negotiation between physics and mortality. The deeper truth emerges here: the barrier to traveling far in one lifetime is not merely distance. It is energy. Kinetic energy increases with the square of velocity. Double your speed, and you need 4 times the energy. Triple it, and you need 9 times the energy. Push toward half the speed of light, and the required energy becomes staggering, approaching the annual energy consumption of entire nations for a single spacecraft. Speed is not free. It is purchased in fuel, in engineering, and in risk. And yet, within that tyranny of speed, there is a narrow corridor of possibility. If humanity masters fusion propulsion, if we build spacecraft capable of sustaining 10 to 20% of light speed safely, then a human lifetime could carry us 10, perhaps 20 light-years from Earth. That is not the galaxy. But it is not nothing. It is a neighborhood of stars, each potentially hosting planets, each potentially harboring oceans, atmospheres, maybe even life. Speed defines the boundary. Physics draws the circle. And within that circle, small though it is, there are real destinations. The stars are not unreachable. They're just expensive. Let's imagine for a moment that we solve the propulsion problem. Fusion works. The engines hold. The spacecraft reaches 10, maybe even 20% of the speed of light. The numbers now look hopeful. A few light-years become reachable. A nearby star system no longer feels mythical. But the moment you approach these speeds, the universe introduces a new character into the story: time itself. At everyday speeds, time feels absolute. Seconds tick the same for everyone. A clock in your kitchen and a clock on a mountain disagree only slightly. But when motion approaches light speed, time begins to bend. Not metaphorically. Physically. Einstein's theory of special relativity tells us something extraordinary: the faster you move, the slower time passes for you compared to someone at rest. This effect, called time dilation, is not speculation. It has been measured repeatedly. Atomic clocks flown on airplanes tick slightly slower than identical clocks left on Earth. GPS satellites must constantly adjust for relativistic time shifts, or navigation errors would accumulate within hours. At ordinary speeds, the effect is tiny. But as velocity climbs toward the speed of light, the difference grows dramatic. At 10% of light speed, time slows only slightly for the traveler. If you journey for 60 years, Earth might experience just a little more, barely noticeable. At 20%, the difference becomes clearer but still modest. You age 60 years. Earth ages perhaps 62. But push toward 50% of light speed, and something profound happens. Now the clocks diverge more visibly. You might experience 60 years while Earth experiences nearly 70. A gap begins to open. At 90% of light speed, that gap widens into something life-altering. 60 years for you could mean well over a century on Earth. The people who waved goodbye at launch would be long gone. Entire generations would have lived and died while you were still traveling. And at 99% of light speed, time dilation becomes extreme. 60 years for you would correspond to more than 400 years back home. Civilizations could rise and fall in that span. Languages could evolve. Borders could dissolve. You would arrive not just at another star, but in another era. This is the strange bargain of relativistic travel. You can stretch your reach across distance, but you stretch time with it. The faster you go, the less you share the same timeline as Earth. There is something poetic about this. Distance and time are woven together in the fabric of spacetime. You cannot pull on one without tugging the other. Now imagine pushing even closer to light speed, 99.9%. At that velocity, time for you slows dramatically. 60 years aboard your spacecraft might correspond to more than 1,000 years on Earth. You could cross dozens of light years within your lifetime, while centuries sweep past the planet you left behind. In principle, if you traveled arbitrarily close to the speed of light, you could traverse enormous distances in a single lifetime from your perspective. You could reach the center of our galaxy, 26,000 light-years away, within decades of personal time, while tens of thousands of years unfold on Earth. You could even cross intergalactic space, arrive at the Andromeda Galaxy in your own lifetime. But when you looked back, the Earth you left would no longer exist as you knew it. Humanity might have evolved, vanished, or transformed beyond recognition. The Sun itself would be older, edging closer to its eventual red giant phase billions of years in the future. Relativity offers distance at the cost of belonging. And there is another constraint hidden in this equation: infinite energy. As your velocity approaches light speed, the energy required to accelerate further grows without bound. It does not simply increase steadily. It skyrockets. To reach exactly light speed would require infinite energy, something the universe does not provide. Anything with mass is forever confined to speeds below light. Light itself travels at light speed because photons have no mass. A spacecraft, no matter how advanced, always will. So, while relativity allows you to stretch your personal lifetime across vast cosmic distances, it does not allow you to break the ultimate speed limit. You can approach it, but never reach it. Each extra fraction of a percent demands disproportionately more energy. This leads to a sobering realization. There are two fundamentally different kinds of interstellar journeys. The first kind aims to stay synchronized with Earth's timeline. You travel at moderate fractions of light speed, 10, 20, maybe 30%. Time dilation is noticeable but manageable. When you arrive at another star, Earth has aged decades, not millennia. You remain connected to your era, but your reachable distance is limited to a few dozen light-years at most. The second kind aims to maximize distance within your lifetime. You push toward extreme relativistic speeds. From your perspective, you can reach astonishing places. But from Earth's perspective, centuries or thousands of years pass. You become a traveler not only in space, but in time. You can go far, but you cannot come home to the same world. For most practical discussions about what humanity might realistically achieve in the next century or two, we remain in the first category. Speeds around 10 to 20% of light speed are ambitious but conceivable with advanced fusion propulsion. At those velocities, a human lifetime could span roughly 10 to 20 light-years. And within that radius lies a small but meaningful collection of stars. Red dwarfs like Proxima Centauri, sun-like stars like Tau Ceti, systems that may host rocky planets in habitable zones where temperatures allow liquid water. It's a tiny bubble compared to the Milky Way's 100,000 light-year diameter. If the galaxy were the size of a continent, your lifetime's reach would cover a few neighborhoods. But those neighborhoods are real. They contain billions of cubic miles of space, entire solar systems, and perhaps ecosystems waiting to be discovered. Relativity does not forbid interstellar travel. It defines its cost. The universe is not hostile to motion. It is structured around limits. The speed of light is not an obstacle placed in our way. It is a property of reality itself, woven into how space and time relate to each other. And within those limits, there is still room for exploration. If we accept moderate relativistic speeds, enough to keep us tethered to Earth's timeline, a lifetime allows us to reach only nearby stars. If we accept the severing of that tether, then distance opens dramatically, but at the price of returning to a future that no longer resembles home. So, how far could you travel in one lifetime? If you want to remain part of your own era, perhaps 10 to 20 light-years with advanced technology. If you're willing to surrender your connection to time itself, then the answer becomes far larger, limited less by lifespan and more by energy. But even in the most optimistic case, even with engines humming at 20% of light speed, the Milky Way remains vast beyond comprehension. One lifetime cannot cross it. It cannot even come close. And yet, for the first time in human history, physics tells us something extraordinary: the nearest stars are not forbidden. They are simply difficult. And difficulty is not the same as impossibility. Let's say the engines work. Let's say humanity builds a fusion-powered spacecraft capable of cruising at 20% of the speed of light. The energy problem is solved. The math checks out. The star is within reach. Now the journey truly begins. And this is where space stops being empty. We often imagine interstellar space as a perfect vacuum, a silent, untouched void. In reality, it is more like an ultra-thin fog stretching between the stars. On average, there is about one atom in every cubic centimeter of interstellar space. That is unimaginably sparse compared to Earth's atmosphere, which contains trillions upon trillions of atoms in the same volume. But when you move slowly, one atom per cubic centimeter feels like nothing. When you move at 20% of the speed of light, it feels very different. At those speeds, your spacecraft is sweeping through billions of cubic centimeters of space every second. Each atom you encounter becomes a microscopic projectile. A hydrogen atom may be tiny, but at relativistic speeds, even something tiny carries real kinetic energy. Multiply that by trillions upon trillions of impacts over years of travel, and the front of your spacecraft becomes a target in a constant, invisible storm. The faster you go, the more violent that storm becomes. At 10% of light speed, each atom strikes with modest energy, individually harmless, collectively heating your ship's forward surface. At 20%, the energy quadruples. At 50%, it becomes extreme. The bow of the spacecraft would glow, slowly eroding under the ceaseless bombardment. It's like driving through rain. At low speed, raindrops feel soft. At highway speed, they sting. At orbital speed, they become needles. At relativistic speed, even dust turns lethal. And dust is the real danger. Interstellar space contains tiny grains of material, microscopic particles of carbon, silicate, ice. They are rare, but not non-existent. A dust grain the width of a human hair weighs almost nothing. But at 20% of light speed, it carries energy comparable to a high-powered rifle bullet. At 50%, it approaches the energy of a small explosive device. You cannot see these grains coming. They are too small to detect from far away. There is no steering around them. At such velocities, impact happens before awareness. A single collision could punch through hull plating, rupture systems, even threaten crew compartments if shielding fails. Over a journey of multiple light-years, the probability of impact is not theoretical. It is inevitable. So, the spacecraft must carry armor. Designs for interstellar craft often include a massive forward shield. Layers of material positioned like a battering ram at the ship's nose. When dust strikes the shield, it vaporizes, dispersing its energy before reaching critical systems. Some proposals suggest placing a cloud of small particles ahead of the ship to intercept larger grains in advance, creating a sacrificial barrier. But shielding adds mass. Mass requires more energy to accelerate. More energy requires more fuel. More fuel increases mass again. The spiral returns. Even if we master propulsion, we must build a vessel capable of surviving years of high-speed collision with the interstellar medium. Space is not a gentle emptiness. It is a thin but relentless resistance. Then there is radiation. Earth is protected by two great shields, its magnetic field and its atmosphere. Charged particles from deep space are deflected or absorbed long before they reach the surface. We live inside a protective cocoon. But in interstellar space, that cocoon vanishes. Cosmic rays, high-energy particles launched by supernova explosions and violent astrophysical events, travel near light speed. When they strike human tissue, they damage DNA, increasing cancer risk and potentially causing radiation sickness over long exposures. Astronauts aboard the International Space Station already receive significantly higher radiation doses than people on Earth, and they are still partially protected by Earth's magnetosphere. A journey lasting decades in deep space would expose the crew to far greater cumulative radiation. Shielding against radiation is difficult. Light materials like water and polyethylene are effective at absorbing cosmic rays, but they must be thick, meters thick, to provide substantial protection. Water tanks might double as radiation shields, wrapped around crew compartments like a moat around a castle. But again, mass grows. Every layer of protection increases the burden on propulsion. Every gram must be accelerated to enormous speed. And radiation is not the only biological concern. Long-duration exposure to microgravity weakens muscles and bones. Astronauts on the ISS must exercise for hours each day to prevent severe degradation. Over 60 years, microgravity could devastate the human body. One solution is artificial gravity, rotating sections of the spacecraft to create centrifugal force, simulating Earth-like conditions. But rotation requires structure. Structure requires mass. Mass requires energy. Even with gravity solved, the human body must endure decades in a closed environment. Air must be recycled flawlessly. Water must be purified endlessly. Food must be grown or stored for years. Mechanical systems must function without resupply or repair from Earth. On Mars missions lasting months, equipment failures already pose serious risk. Multiply that by decades, and the margin for error becomes razor-thin. A minor malfunction in year 2 could become catastrophic by year 20 if spare parts run out. And then there is the mind. Imagine living inside a metal vessel for 60 years. No open sky, no wind, no horizon. Only walls, corridors, recycled air, and the quiet hum of machinery. Human beings evolved in open environments. We are creatures of landscapes, seasons, weather, sunlight shifting across terrain. In isolation studies, Antarctic stations, submarines, even space stations, psychological strain becomes evident after months, irritability, depression, conflict. Now extend that confinement across a lifetime. Communication with Earth would grow slower as distance increases. At 1 light-year away, a message takes 1 year to arrive, and 1 year for a reply. At 10 light-years, 20 years for a round trip. Conversations dissolve into historical correspondence. You send a message in youth and receive the reply in middle age. You cannot call for help. You cannot turn around easily. You are committed. The crew must remain not only physically healthy, but socially stable for decades. Conflicts must be resolved. Purpose must be maintained. Motivation must survive monotony. We have never tested human psychology under those conditions. All of these hazards, dust, radiation, mechanical failure, psychological stress, exist regardless of propulsion technology. They are not optional challenges. They're inherent to traveling at relativistic speeds through interstellar space. And yet, none of them violate physics. They are engineering problems, difficult, enormous, but solvable in principle. The deeper message here is this: reaching another star is not a single breakthrough. It is a chain of breakthroughs. Propulsion, shielding, life support, psychology, energy production. Every link must hold. A failure in any one breaks the mission. Interstellar travel is not impossible. It is unforgiving. If humanity develops fusion propulsion capable of 20% of light speed, and if we design shielding strong enough to withstand decades of impacts, and if we solve radiation protection, artificial gravity, life support, and social stability, then a human lifetime could carry us perhaps 20 light-years from Earth. But only if all of it works. The universe is not stopping us with a wall. It is testing us with a series of escalating demands. And those demands remind us of something essential: distance is not conquered by speed alone. It is conquered by endurance. To travel through space in one lifetime is not simply to go fast. It is to survive the journey. And survival in the cold between stars is the real frontier. So far, we've measured the universe against a single human lifetime. 60 years of motion, 60 years of breath and heartbeat carried through the dark. But what if the limitation isn't speed alone? What if the constraint is the lifetime itself? There is another path to the stars, one that does not rely on extreme velocities or flirting with the speed of light. Instead of trying to compress distance into one lifetime, you stretch the lifetime across distance. You build a world that travels. This is the idea of the generation ship. Imagine a spacecraft not the size of a capsule, but the size of a small city. Not a vehicle you board for a trip, but a habitat you're born into. It rotates slowly, creating artificial gravity through centrifugal force. On its inner surface are homes, farms, forests under artificial light, reservoirs of water. Children run beneath curved skies, never realizing the ground beneath their feet is metal. The ship travels at a modest speed, perhaps 1 or 2% of the speed of light, slow by relativistic standards, but fast compared to anything we have achieved so far. At 1% of light speed, the journey to a star 10 light-years away would take about 1,000 years. At 5%, 200 years. No single person would see both departure and arrival. The people who launched the ship would die en route. Their children would grow old aboard it. Their grandchildren might be the ones who finally see another sun swell large in the forward viewports. From a physics perspective, this is far easier than trying to push toward 20 or 30% of light speed. Energy requirements fall dramatically. Radiation hazards are more manageable. Interstellar dust becomes less violent. The engineering, while immense, feels less like defiance of nature and more like extension. But generation ships trade velocity for complexity. To survive for centuries in isolation, the ship must be self-sustaining. Not for months like the International Space Station, not for years like an Antarctic base, but for lifetimes upon lifetimes. Everything must be recycled. Air must be regenerated. Water purified endlessly. Soil nutrients restored. Nothing can be wasted, because nothing can be resupplied. You're building a closed ecosystem in space. We have tried something similar before. In the early 1990s, a project called Biosphere 2 sealed 8 people inside a self-contained habitat in Arizona, attempting to simulate a closed ecological system. It lasted 2 years. Oxygen levels fluctuated. Carbon dioxide spiked. Food production struggled. The balance of nature proved harder to recreate than expected. And that was on Earth, with gravity, sunlight, and emergency support just outside the door. A generation ship would have none of that safety net. Then there is genetics. A small population isolated for centuries faces inbreeding risks. Harmful genetic traits can accumulate. To maintain healthy diversity, the starting population must be large, perhaps hundreds, maybe thousands. That increases the size of the ship. The size increases the mass. The mass increases the propulsion challenge. The social dimension is even more fragile. Imagine being born aboard a ship whose destination you will never see. Earth exists only in stories and recordings. The star you're traveling toward is a promise made by ancestors long dead. What happens if 200 years into the journey, a generation decides the mission no longer matters? That they prefer to remain aboard their rotating world rather than risk landing on an unknown planet. A generation ship must not only sustain biology, it must sustain belief. Civilizations on Earth have collapsed in far less isolation. Revolutions, conflicts, power struggles. These are part of human history. In the sealed environment of a starship, there is no external frontier to escape to, no new continent to relieve tension. Social instability could doom the mission long before physics does. Yet, despite all these challenges, the generation ship offers something extraordinary. It removes the pressure of a single lifetime. Instead of asking how far one person can travel, it asks how far a civilization can reach. And that shifts the scale dramatically. At even 1% of light speed, given enough centuries, you can cross dozens of light years. Given millennia, you can traverse significant portions of the galaxy. Not in a burst of heroic acceleration, but in slow, patient expansion, like seeds drifting on the wind. This model changes the emotional calculus. A relativistic ship is a one-way arrow through time. It sacrifices connection to the present in exchange for distance. A generation ship sacrifices immediacy instead. It asks for continuity, commitment, a belief that the journey itself is meaningful. In some ways, it mirrors how humanity has always expanded. The first settlers who crossed oceans in wooden ships rarely knew exactly what they would find. Some did not survive. Others arrived and built new societies that looked little like the old ones they left behind. The difference is that oceans can be crossed in weeks. Interstellar space demands centuries. There is also another idea that often appears alongside generation ships: suspended animation. If humans could be placed into a state of deep cryogenic sleep, metabolism halted, aging paused, then the journey could span centuries while feeling like days to the travelers. You could leave Earth, sleep through the dark, and awaken around another star as if no time had passed. Biology, however, is far less cooperative than physics. We can freeze cells. We can preserve embryos. Certain small organisms survive freezing by entering dormant states. But freezing a complex mammal without destroying its tissues has never been achieved. Ice crystals rupture cells. Rewarming causes further damage. The human brain, with its delicate web of neurons encoding memory and identity, is especially vulnerable. Cryonics organizations preserve bodies today, hoping future technology might revive them. But revival has never been demonstrated. It remains speculative, a wager placed against time. If suspended animation ever becomes possible, it would bridge the gap between single lifetime travel and generational voyages. You would not need vast rotating cities. A smaller crew could sleep through the journey, awakening upon arrival. But until such technology exists, the generation ship remains the most conservative path across great distances without extreme speed. And here is the critical distinction. A generation ship allows humanity to reach far beyond what one lifetime permits, but it does not allow one individual to travel that far. The question we began with was personal: how far could you travel in one lifetime? The generation ship answers differently: how far could we travel if we're willing to think in centuries? For the individual, physics and biology confine you to perhaps 10 or 20 light-years with foreseeable propulsion. For civilization, patient and collective, the reachable horizon expands dramatically. The galaxy does not demand speed. It demands time. And perhaps that is the deeper lesson. The stars are not necessarily unreachable. They are simply far enough that they test our sense of continuity. To cross those distances may require us to redefine exploration, not as a single heroic journey, but as a chain of lifetimes linked together. One lifetime can reach a handful of stars. Many lifetimes bound together in purpose could reach far more. And in that difference lies the choice between a voyage and a legacy. After all the engines, all the equations, all the daring concepts, we return to something simple and human, a clock. Not the clock in a laboratory. Not the atomic clocks that measure relativity. Your own biological clock. A life that begins, unfolds, and ends in roughly 8 decades. If you leave young, perhaps 60 of those years could be spent traveling fully conscious, watching the stars slowly rearrange outside your window. So, what does that clock actually buy you? With the technology we possess today, it buys you the outer edge of home. You could pass Mars, sweep beyond Jupiter, slip past the icy frontier of Neptune. You could cross the heliosphere and enter true interstellar space. You would become one of the few humans to leave the sun's protective bubble. But you would not reach another star. Even moving faster than any spacecraft ever built, you would spend your entire lifetime crossing only a tiny fraction of the gulf to Alpha Centauri. The nearest stellar neighbor would remain almost exactly as distant when you die as when you began. That is not a failure of courage. It is a statement about scale. But imagine humanity advances. Not recklessly, not magically, but step by step. Nuclear propulsion matures. Fusion becomes stable and compact. We learn to shape starfire into thrust. At 10% of light speed, 60 years carries you roughly 6 light-years. That distance includes Barnard's star. It includes several dim red dwarfs, each with its own retinue of planets. You would leave the sun behind not as a symbolic gesture, but as a measurable displacement. Earth would no longer be your nearest star. At 20% of light speed, the sphere doubles. Now your lifetime spans about 12 light-years. Within that radius lie dozens of stellar systems. Not mythic lights in the sky, actual suns with gravitational families. Some of them likely host rocky worlds in temperate orbits. Some may have atmospheres thick with clouds. Some may be barren and silent. But they are reachable. Not easily, not cheaply, but physically reachable. That is the realistic horizon of a single human life. Somewhere between 10 and perhaps 20 light-years, if we build the right engines and survive the journey. And that distance, small as it sounds, changes everything. Because once you stand beneath another sun, even a dim red dwarf glowing like an ember in a black sea, you have crossed a boundary no human has crossed before. You have stepped outside the solar system, not as a drifting artifact, but as a living being. You have proven that humanity is not permanently anchored to one star. You have redrawn the map of what is possible. Beyond that range, the galaxy stretches almost mockingly vast. The Milky Way is 100,000 light-years across. A reachable bubble would be a speck in its spiral arms. If the galaxy were the size of Earth, your lifetime would cover only a small region of coastline. You cannot roam freely among its hundreds of billions of stars. You cannot wander from arm to arm, visiting nebulae and black holes like tourist attractions. The galactic center, 26,000 light-years away, remains unreachable. Other galaxies, Andromeda, Triangulum, are fantasies measured in millions of light-years. Those distances are not just large. They are beyond the budget of a mortal lifespan. Unless you surrender time itself. If you travel at extreme relativistic speeds, near light speed, your personal clock slows dramatically. You could cross greater distances within your own lifetime. But Earth would race ahead. Decades would become centuries. Centuries would become millennia. You would not return to the world you left. You would arrive in a future that has erased you. That is the hidden clause in the contract of near-light travel, distance in exchange for belonging. So when we ask how far you can travel in one lifetime, the answer splits into two paths. If you want to remain part of your own era, connected to the civilization you departed, the horizon is modest, 10, maybe 20 light-years with optimistic future technology. If you are willing to let centuries pass behind you, then the reachable distance grows, but the world you knew dissolves. Either way, the universe does not grant infinity. And yet 10 or 20 light-years is not nothing. Within that sphere are potentially hundreds of planets. Within those planets, the possibility, however small, of oceans beneath alien skies, of biology shaped by different suns, of chemistry that wrote its own story. You do not need the whole galaxy to ask the biggest question humanity has ever asked: are we alone? That question can be answered in our immediate cosmic neighborhood. So perhaps the more honest way to frame this is not how far can we go, but is that far enough? A single lifetime cannot conquer the Milky Way. It cannot roam among its spiral arms like a traveler crossing countries. But it can break the seal of isolation. It can carry a human being from one star to another. For all of history, that possibility was indistinguishable from fantasy. Now it is a matter of engineering. The universe has drawn a boundary around each life. It has limited our speed, fixed our mortality, woven space and time together so tightly that neither can be stretched without consequence. But within that boundary, there is still room to move. In one lifetime, you may never see the far edge of the galaxy. You may never witness the birth of distant quasars or drift between galaxies in the dark. But you could leave the sun. You could reach another star. You could stand beneath alien light. And that is not a small thing. Because the first step between stars is not measured in thousands of light-years. It is measured in the courage to cross the first few. A lifetime, it turns out, is long enough to begin. The farthest distance from Earth you could realistically travel in one lifetime, if humanity achieves advanced fusion propulsion, is approximately 20 light-years.